It's time to extend our discussion of digital communication systems a little bit more. We start with a message signal, x of t. This is a continuous analog signal with a bandwidth b. b is the highest frequency component in x of t. That's applied to a sampling circuit controlled by a clock which sets the sampling rate f sub s. To reconstruct the original signal from the samples, the sampling rate has to be greater than or equal to twice the bandwidth of the original signal. The sampled signal is then applied to a quantizer, which uses a certain number of bits to express each sampled value digitally. So it rounds off the sampled value to the nearest standard level. That depends on the number of bits used and the number of levels used. The number of levels is 2 to the power of n, where n is the number of bits. This is where quantization noise is induced into the quantized signal. The quantized signal is then encoded as a digital signal, a binary signal. Well, I'm saying a digital signal. It's a string of ones and zeros, a random string of ones and zeros. It's a binary signal. More than that, it's a random binary signal. We'll take the probability of 0 equal to the probability of 1, both being equal to 1/2. The bits proceed at a certain number of bits per second. That's the bit rate. The bit rate is equal to the sampling rate times the number of bits per sample. And each bit is transmitted for 1 bit period. The bit period is equal to the reciprocal of the bit rate. So if the bit rate is bits per second, the bit period is the number of seconds per bit. And this we have coming out of the encoder the baseband digital signal. This signal is encoded using one of the schemes perhaps that we discussed last time, one of these several schemes of encoding logical ones and logical zeros. And it makes a difference which one you choose because they have different spectral characteristics. They have different bandwidths and other spectral characteristics. So we want to extend this system now by taking this baseband digital signal m of t. So we're going to take m of t, that's this signal, and now we are let's see, we have to apply this to a modulator where we take a carrier signal, and we modulate the carrier signal in some fashion using this baseband digital signal. And what the result is, we'll call this again phi of t. This is a modulated signal that will then be transmitted so there's some kind of transmission medium, and it then goes to a receiver, I before E except after C, to look that up. A receiver, then a demodulator, that will reverse the effects of the modulator, so we can get a demodulated signal out. There's the dogs barking again. And that will be followed by a decoder, perhaps we can call it. Something that will take our encoded digital signal and turn it back into a string of ones and zeros. And that would then be followed by a digital to analog converter. And the result of this will be a replica. I'm going to put a hat above it to indicate that it is a replica of the original message signal. It's never going to be exactly the original message signal because of the quantization noise, which is still going to be turned up as noise in this reconstructed signal. Okay, I can't think of any other factor that would make it not exact, presuming that it's been sampled properly. And apart from amplification and perhaps a bit more filtering or equalization, frequency equalization or something, this would be a replica of x of t. Now, in practice, this replica is close enough that that our ears can't tell the difference, or it's close enough that we can extract the information that we wish to extract from the signal. Okay, so now for the next few pages, I want to look more closely. Modulator. This is modulator. Okay, I want to look more closely at this modulator, and then a bit perhaps at the demodulator. Demodulator. Okay, there we go. You can tell I'm doing this live on tape. So for our first modulation system, let's consider the simplest of the encoding, the unipolar non-return to zero. Logical ones are 1 volt, logical zeros are 0 volts. We will apply this signal to a mixer. This is a multiplier, and we'll mix it with a carrier signal, a sinusoidal carrier signal, amplitude AC, frequency F sub C, and the signal that comes out is OOK, stands for on-off keying, and it will essentially be an amplitude modulated signal. So the output of the mixer is the input signal M of T times AC cosine 2 pi FC T. Okay, and this is exactly the same kind of equation we had for double sideband amplitude modulation. Not large carrier, this is a suppressed carrier. Okay, that's the first form of modulation we looked at many moons ago. Okay, now to see what this let's see what this looks like graphically. This is an example message signal. So this is the signal M of T. Logical ones are encoded as 1 volt, logical zeros as 0 volts. Here, this is the indication of the bit period, and it is a random string of bits: 110, I'm sorry, 111001011001010, etc., etc. So this is the message signal, and the carrier signal just as we've seen before, the carrier signal is AC times the cosine of 2 pi FCT, and I've chosen a carrier frequency so that the pictures that this MATLAB program generates are useful and nice to look at, I suppose. So now we want to look at the modulated signal. Phi of t is equal to m of t times the cosine, let's see, I left out, times AC times the cosine of 2 pi FCT. Chosen an amplitude of 1 to make life simple. And so we're multiplying this carrier times this digital message signal. So where the digital message signal is a 1, we will get the carrier full size. Here's the carrier multiplied by 1, and those regions where the message signal is 0, the carrier is zeroed out. That's why this is called on-off keying. Either the carrier signal is on or it's off, as directed by the 1s and the 0s in the message signal. Okay, and this is what the modulated signal looks like, and it is clearly amplitude modulated. So this is clearly amplitude modulation. It looks a bit like single sideband amplitude modulation taken to an extreme with either 1s or 0s. And coincidentally, this is similar to the signal that would be generated with the 1800s age telegraph. And the Bell Company investigated this kind of signal pretty intensely, and it was the first high-frequency communication type signal that was investigated because it was used in the first long-distance communication system invented, namely the telegraph. Okay, so this is so now let's look at the frequency content of these signals. This is the frequency content of the on-off keyed signal. Remember, we have a carrier at a constant frequency, so the spectrum of the carrier signal is simply a pair of delta functions at the carrier frequency, which I've chosen to be 40 Hertz because just because it made the pictures look nice, or I could get reasonable pictures. This is plus and minus the carrier frequency, and now the spectrum of the binary signal, the unipolar non-return to zero binary signal. We worked this out mathematically, and see if I can find the picture. There it is. This is the picture that we worked out mathematically for this type of binary signal. We've got a component at 0 Hertz. We've got this sine squared shape, and it has a null at equal to the bandwidth to the first null is equal to the bit rate. Well, I took this random signal, did a Fourier transform of it in MATLAB, and this now is what MATLAB returned as the Fourier transform of my binary signal. See, it says here it has this line. This is the DC component. It's shown right here, and then the rest of the spectrum takes this sine squared has an envelope given by this sine squared shape. The reason it's not a smooth line is because it would be had I taken a lot of Fourier transforms and then took the average value, but since I just took the Fourier transform of one sample, I get this this randomization here. But you can clearly see the outline follows the sinc squared. Here is the first null that gives us a bandwidth of the bit rate. So just like single sideband, we're taking a carrier signal and we're mixing it with a message signal. And just like with single sideband, we're going to get the spectrum of the message signal replicated and translated and centered at the carrier frequency. So we're going to be convolving this spectrum with the spectrum of the carrier, and this is the result we get for the spectrum of the modulated signal. It's centered at the carrier frequency. It's got a strong component at the carrier frequency because the baseband signal has a strong component at 0, and that gets shifted and centered at the carrier frequency. And the bandwidth of the modulated signal is equal to twice the bit rate of the digital signal. That's the bandwidth between the first nulls. Now, to demodulate this signal, if we look back again at the modulated signal, I think we can see the easiest way is what we want is we want to recover this envelope, which will give us the binary signal. And the easiest way to do that would be with a peak detector. So it's quite simple or straightforward to demodulate. We take the modulated signal. We need to tune in to we need to have a bandpass filter to tuned to the carrier frequency, the bandpass filter. So its center frequency, the center frequency of the bandpass filter would be equal to the carrier frequency of the modulated signal, and the bandwidth, I call it B0. The bandwidth has to be wide enough to pass the bandwidth of this modulated signal, so it's got to be equal to twice the bit rate. And then that will isolate our modulated signal from whatever other signals are in this same transmission line or being broadcast over the air. Then we have a rectifier, half wave or full wave probably doesn't make much difference. And then we need a low pass filter. You see, so the rectifier will give us the shape of the message signal. The low pass filter will filter out all of the high frequency wiggles, and we don't need to worry about a DC offset since our binary signal has a DC offset, but perhaps a comparator circuit to square up the signal, and what will then be retrieved is our binary message signal. Now it is still encoded. It is still encoded in this unipolar non-return to zero. So it may be a bit of a challenge to decode the ones and the zeros, mainly because we don't have any synchronizing information, and it might be difficult to tell if this is a single 1-bit or if it's a 2 1-bits in succession, or in this case 3 1-bits in succession. Decoding this is a bit of a challenge, but there must be a good way that perhaps you can think of one day. Okay, so this is on-off keying, which is simply amplitude modulation. Let's consider on-off keying again, but this time with a return to zero signal, so that our message signal is for logical 1 has a value of 1, and then halfway through the bit period it returns to 0. And logical 1 has a value of 1, halfway through the bit period returns to 0. Logical 0 is always 0, so this is 1 1 0 1 1 1 0 0 0, etc. This is the message signal in the unipolar return to 0 format. The carrier signal is AC times the cosine of 2 pi FCT, just as before. And we're again mixing the two together in a frequency mixer, so they multiply the two signals. This would be M of t times AC cosine 2 pi FCT. That's the result of the mixer, which again will look like this. The carrier switched on when the message signal is a 1. Carrier is switched off when the message signal is a 0. So this is the modulated signal, phi of t. Well, let me write it the way it shows here. Phi on off key. Phi on off key of t is equal to M of t times AC cosine 2 pi FCT. Okay. Now, if we investigate the spectrum of this signal, again the carrier signal, simply a constant sinusoid, has delta functions at plus and minus the carrier frequency, as we expect. We worked out the power spectral density for the unipolar return to 0. I'm looking for it now. There it is. This is what the mathematics tell us about this this signal. It's got components at DC, and then it's got components at the bit rate, and at 3 times the bit rate some of these get zeroed out. The even harmonics get zeroed out, the odd harmonics remain, and their weight takes the shape of this sinc squared function, and on top of that is this sinc squared function in the background as well that has a null at 2 times the bit rate. That's what the mathematics tell us. This is what I found numerically by taking this random signal and doing a Fourier transform in MATLAB, and we see we get exactly the same result. Here is the DC component. This strong line and this strong line. This is at the bit rate, and then we get the 3rd, 5th, 7th. We get the odd harmonics continuing, and then we also get this. The envelope for this would then be a sinc squared signal, with the first null occurring at twice the bit rate. So this is precisely the same result as we got theoretically. Now, when we take a message signal that has a spectrum that looks like this, and we mix it with a carrier signal that has a spectrum that looks like the pair of delta functions, the convolution will take this this structure and will reproduce it, shift it, and center it at the carrier frequency, plus and minus the carrier frequency. So I had MATLAB take the fast Fourier transform of this modulated signal, and the result is exactly at what we expect. We get this shape replicated and centered at the carrier frequency at 40 Hertz, and at the minus the carrier frequency we've got a strong component at the carrier frequency that corresponds to the DC component, and we've got these two components as well, and all of the odd harmonics. Now it's a bit unrepresentative, I think I should say, because I chose the frequencies because they made reasonable looking pictures, but you can tell that when you take this and replicate it here, you're getting some of this stuff, this part of the signal that would overlap part of the signal from this other shifted version. So there's a bit in this numerical simulation that doesn't quite reflect reality, and I think that's why this line and this line are shorter than the other two lines. It's because of the numerical limitations of my numerical simulation. But we get the spectrum just as we would expect with an amplitude modulated signal. Now this one happens to have a strong component at the carrier frequency. That's useful because that will make it easier to tune in to the signal spectrum that we're looking for. And it's also got these two components, which are useful as well. Okay. So now for demodulation, I think what I would suggest might be a good way, if we take this on-off keyed signal, then how about this? We mix with a replica. We mix with a replica of the carrier signal. That will shift this signal back down to this location. So we follow that with a low-pass filter. The bandwidth of the low-pass filter has to be wide enough. It's got to be twice the bit rate, and that will recover the spectrum of this composite signal, which will recover our message signal M of t. Now, what we also get, though, since this signal will have these two strong lines at the bit rate, we can take this message signal, recovered message signal, into a bandpass filter that has a center frequency equal to the bit rate, so we can tune in to this strong line and this strong line. This would have to be a narrow bandwidth for this bandpass filter, and what we would get out of this bandpass filter then would be a kind of a sinusoidal type signal that would be that would have a frequency equal to the bit rate. So we take this into a comparator, and what comes out of the comparator would be a clock signal. You may have to do some time shifting to get things synchronized correctly, and what we then recover is a clock. Okay, this is one of the advantages of this return to zero signal, is that we can recover a replica of the clock signal, which could be helpful in decoding the digital signal. Okay. Now the price you pay for being able to recover the clock signal is that the modulated signal requires more bandwidth. It requires bandwidth equal to 4 times the bit rate.